Picture the ocean from far above, the way a satellite might see it. From that height, the water looks calm and blue, almost gentle, like a smooth sheet pulled tight over something enormous. You would never guess, just from that quiet surface, that beneath it lies a canyon deeper than any on land, a crack in the earth, so deep that the tallest mountain on the planet could sink into it and still leave water above its peak. This is the Mariana Trench, a long scar in the floor of the western Pacific Ocean. At its deepest point, called Challenger Deep, the water goes down almost 11 kilometers. That is close to the cruising height of a passenger jet, only turned upside down and filled with black water instead of open sky. If you could fold that whole column of ocean between your palms, you would feel the shape of a distance that swallows light, sound, and warmth long before it reaches bottom. Lower yourself into that water, even in imagination, and the world changes fast. Within the first few hundred meters, sunlight starts to fade into deep blue, then into a blue so dark it feels closer to black. By 1,000 meters, no light from the sun reaches you at all. Not dim light, not filtered light. None. Your eyes would strain uselessly in a dark that has been permanent and complete for longer than humans have existed. Before we go further, the planet has a new, quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. The deeper you go, the more the water itself seems to lean against you. At the surface, air presses on your body with a weight you never notice, since you have felt it your whole life. Scientists call this 1 atmosphere of pressure. At the bottom of the Mariana Trench, the pressure climbs to more than 1,000 atmospheres, over 11,000 times what you feel right now, standing or lying still on land. The number is easy to say and almost impossible to picture. It is the kind of scale that makes the mind reach for something familiar and find nothing that fits. If your body could somehow reach that depth unprotected, the first danger would not be running out of air. It would be pressure itself, pressing equally on every surface of you at once, on the air pockets in your lungs and sinuses, on the spaces the human body was never built to keep sealed at that force. Researchers who study deep sea physiology describe this as a whole body event, not a slow suffocation. The idea remains grounded in physics we understand well, even though no person has ever tested it directly and lived to describe the feeling. Descending to that depth by submersible does not happen quickly. It takes hours of steady sinking through darkness, the vessel's lights carving a small lonely circle in the black water. Outside that circle, there is nothing to see, only the occasional pale shape of a creature built for a world with no sun. Some researchers wonder if the slowness of that descent matters as much as the depth itself, giving the body time to adjust in ways a sudden drop never would. Others argue speed changes little, since the pressure at the bottom would overwhelm a human body regardless of how gently it arrived. At the very bottom, the water sits just above freezing, and the cold there is patient rather than sharp. The seafloor itself is soft, made of fine sediment that has drifted down from far above for millions of years, undisturbed by waves or wind or any hand that has touched it. If you stood on that floor, the ground beneath your feet would give slightly, like walking on wet ash that has never once been touched by sunlight. Life exists down there, quietly and strangely, adapted to that crushing weight in ways scientists are still working to fully understand. Some creatures found near the trench floor do not simply tolerate the pressure. They seem to need it, and brought up toward the surface, their bodies fail in the opposite direction, as if the emptiness above were its own kind of danger. Whether this dependence is universal among deep-trenched life, or whether some species could adjust given time, remains an open question in marine biology. All of this sits at the bottom of a hole in the ocean that few humans have ever seen with their own eyes. Fewer people have reached the deepest point of the Mariana Trench and have stood on the surface of the moon. Tonight, we will sink slowly into that distance together, not to solve it, but to sit quietly at its edge and wonder what it would feel like for just a moment to be there. Your body is built for a thin slice of the world. Close your eyes and think about the deepest pool you have ever swum in. Maybe it came up to twice your height. Even there, you likely felt a small ache in your ears, a signal your body sends when pressure changes even a little. That ache is your first honest lesson in how narrow your comfort really is. Air presses on you all the time, though you rarely notice it. At sea level, that pressure has a name. Scientists call it 1 atmosphere, a unit built around the weight of the air above your head, your lungs, your blood, the small air pockets in your sinuses. All of it sits in balance with that steady push. You do not feel it because you have never known anything else. Water changes the math quickly. For every 10 meters you descend, about 33 feet, the pressure rises by another full atmosphere. At 10 meters, you feel 2 atmospheres pressing on you. At 23, a recreational scuba diver might go to 18 or 20 meters and feel a noticeable squeeze in the mask and ears. A trained technical diver might push past 60 meters into cold, dim water, breathing carefully mixed gas to keep their body from turning against itself. Beyond that point, human tissue starts running out of room to compromise. If you dropped straight down into the Mariana Trench, the deepest known point in any ocean, you would travel almost 11 kilometers before touching the bottom. Picture a commercial jet cruising at its normal altitude. Now imagine that same distance stretching downward instead of upward into cold and utter dark. At the bottom of that drop, the pressure would reach around 11,000 times what you feel right now, standing or lying comfortably wherever you are. That number is easy to say and hard to hold in your mind. One way to feel its size is to imagine standing under the weight of about 50 jumbo jets, stacked and pressing down on every square inch of your body at once. Another is to picture wearing the full weight of the Eiffel Tower on your shoulders, spread evenly across your skin. Neither comparison captures it fully. The pressure at that depth acts everywhere, all at once, inside you and outside you, with nowhere for it to concentrate or hide. Here is the part that surprises most people. Crushing is not really the danger, not in the way falling rock might crush a bone. Water pressure pushes evenly from every direction. Your body, mostly made of water itself, resists that even pressure fairly well. The real trouble lies in the air pockets, your lungs, your sinuses, the middle space behind your eardrums. All hold gas that compresses far more easily than liquid or solid tissue. As you sink, those pockets would shrink first, unevenly, faster than the rest of you could adjust. Some researchers who study diving physiology describe this as the body's real limit, the mismatch between compressible air and incompressible tissue. Others point to a second, quieter danger: gases dissolving into your blood under pressure, then behaving strangely as pressure shifts again. Both ideas agree on one thing: long before crushing itself becomes the main event, your body's relationship with air breaks down completely. Unaided, and without equipment, a human descending past a few hundred meters would lose consciousness, and the body's own structure would begin to fail, well before reaching anything like the ocean floor. If you tried this yourself, without protection, the ache in your ears at the 10-meter mark would be the mildest warning your body could give you. Past, that the feeling would shift from discomfort to genuine danger within moments. Engineers who design deep submersibles spend enormous effort solving this one problem: how to carry a pocket of 1 atmosphere air down into a place where the water outside wants to flatten anything hollow. Thick metal spheres, careful seals, redundant systems. All of it exists because your body simply was not built to negotiate with that kind of pressure. We tend to think of the ocean as an extension of the beach, just deeper and colder. The truth is stranger. Somewhere below the reach of sunlight, your body's whole relationship with the world it knows starts to dissolve. The line between where you could survive and where you absolutely could not is not far below where casual swimmers already float. If you stood at that line, in the last shallow water where you could still breathe on your own strength, you would already be close to the edge of everything your body understands. Picture yourself floating just below the surface of the open ocean. Your body feels almost nothing there. The water holds you gently, and the pressure on your skin is barely different from the air above. Now, imagine sinking. For every 10 meters you drop, the water above you adds another full unit of pressure, equal to the whole weight of the atmosphere pressing down at sea level. This is not a sudden event. It is a slow accumulation, layer by layer, kilometer by kilometer, until the numbers become almost impossible to picture. The ocean did not always press down this hard. 4 billion years ago, Earth's water was still arriving, delivered by comets and released from cooling rock, filling basins that had only just begun to form. Over time, as the seafloor spread and continents drifted, some basins deepened far beyond the rest. The Mariana Trench in the Western Pacific formed where one tectonic plate, a piece of Earth's outer shell, slides beneath another, bending down into the mantle below. This process, called subduction, is slow even by geological standards, unfolding over tens of millions of years. As one plate sinks under another, it drags the ocean floor down with it, carving a scar in the earth nearly 11 kilometers deep. Standing at the rim of that trench, you would not see a canyon the way you might on land. There is no cliff face to look over, no rush of vertigo. The floor of the ocean simply keeps sloping downward, farther than sunlight has ever traveled, until it reaches a place still forming today, still shifting, still being pressed by the plates that made it. The water filling that trench did not arrive all at once either. It settled in over millions of years as the basin deepened, cold and dense water sinking from the surface, pooling into the lowest points Earth's crust could offer. Each new meter of water added its own quiet weight to all the water above it. By the time you reach the bottom, roughly 11 kilometers down, that stacked column of seawater is pressing with a force about 11,000 times what you feel simply standing outdoors. Your body was built for 1 unit of pressure. It was never built for 11,000. One theory about why life persists at such depths at all is that pressure itself is not the enemy scientists once assumed. The water pressing on a body from every direction is not like a hand crushing a chest. It is even, constant, applied to every cell at once, rather than concentrated in one place. Soft tissue, mostly water itself, resists this kind of pressure surprisingly well. The real danger, most researchers agree, lies elsewhere, in the air spaces the human body carries with it. Lungs, sinuses, the small pocket of air behind an eardrum. These are the places where the mismatch between inside and outside becomes violent. A competing line of thinking focuses less on the water and more on the geology itself, on how young and active this stretch of ocean floor still is. Some researchers studying the trench wonder whether its extreme depth is not simply a record to be measured, but a live process, still deepening in small increments as the plates continue their slow collision. If that is true, the 11 kilometers we measured today may not be a fixed number at all. It may be one point in a process that started tens of millions of years ago and has not yet finished. What remains unresolved is how completely we understand the forces at play down there, even after decades of measurement. Pressure sensors and sonar readings tell us the shape of the trench with real precision. But the deep interactions between crushing pressure, near freezing temperature, and complete darkness, working together on living tissue over long periods, are still being studied piece by piece. No one disputes that the numbers are real. What stays open is how fully those numbers explain everything that happens to a body or a machine once it crosses into that depth. If you could somehow stand at the very bottom of that trench, boots on soft sediment, the water above you would not feel like water anymore in any ordinary sense. It would feel like the accumulated memory of every drop that ever fell into that basin, every meter of descent stacked silently overhead. It took the planet tens of millions of years to press that basin down to its current depth. It would take your body perhaps a single moment to learn what all that weight actually means. Picture the air in your lungs right now. It feels like nothing. It weighs almost nothing. It is a mix of nitrogen and oxygen, mostly, drifting in and out without effort. If you carried that same breath down into the Mariana Trench, something strange would happen to it long before you reached the bottom. The air would not stay air under. Enough pressure, gas behaves differently than it does at the surface. It compresses. It dissolves into blood and tissue in ways it never would up here. Somewhere on the way down, the air you know would stop behaving like something you can breathe and start behaving like something else entirely. The water pressing in around you, meanwhile, carries its own long history. Most of Earth's ocean water likely came from inside the planet itself, released slowly over billions of years by volcanic activity as the young Earth cooled. Some scientists think part of it may have arrived later, delivered by icy comets or water-rich asteroids colliding with the early planet. Both ideas remain live possibilities, and researchers still debate how much came from where. Either way, the water now pressing against a submersible hull at 11 kilometers down began somewhere far from that spot, sometimes far from this planet's own formation. The salt dissolved in that water has its own quiet origin story. Rain falling on land dissolves minerals from rock, and rivers carry those minerals to the sea over immense stretches of time. The ocean has become salty the way a cup of tea becomes sweet, one slow spoonful at a time, except the spoonfuls took hundreds of millions of years. That salt is not decoration. It changes how water behaves under pressure, how it freezes, how it carries sound. At the bottom of the trench, you would be surrounded by an ancient chemical solution, built one river at a time. Go deeper into the ingredients, past water and salt, and you reach the iron. Earth's core, roughly 6,000 kilometers beneath your feet as you stand at the trench floor, is mostly iron and nickel. That iron did not form here. It was forged inside dying stars, in the final violent moments of their lives, long before our sun or planet existed, when those stars scattered their contents into space. Some of that material eventually gathered into the cloud of dust and gas that became our solar system. The iron pulling the ocean into a sphere, the iron inside your own blood, both trace back to the same collapsing stars. The pressure crushing down on the trench floor exists because gravity, working on all that ancient stellar material, pulled Earth into a dense, layered ball. The pressure itself is not a mysterious force with no explanation. It is simply weight, water stacked 11 kilometers high, each layer pressing on the layer below. At the surface, air alone gives you the pressure equal to 1 atmosphere. Add 11 kilometers of seawater above your head, and the number climbs to roughly 1,100 times that, more than 15,000 pounds, pressing on every square inch of you. Physicists can write that number cleanly on a page. It follows simple, well-understood rules of fluid pressure. And yet, no equation captures what such total, equal pressure would feel like distributed through living tissue, because no living human body has ever gone there unprotected to report back. This is where the open question sharpens. We can trace the iron to dying stars. We can trace the water to a volcanic Earth or to arriving comets. We can calculate the pressure to the pound, but the deep ocean floor still holds questions no formula answers. Scientists do not fully agree on how much water Earth captured during formation versus how much arrived later. They do not fully agree on exactly how the deepest trenches formed, though subduction, where one piece of Earth's crust slides beneath another, is the leading explanation. Even something as basic as the total volume of the deep ocean floor that remains unmapped in fine detail is still being revised as survey ships slowly fill in the picture. If you held a glass of that trench water in your hand at the surface, it would look ordinary, clear, unremarkable. You would never guess it carries salt from 1 billion years of rivers, was shaped by iron born in a star, and moves under a pressure your ribs were never built to hold. Every material at that depth has a story stretching back before the ocean, before the planet, in some cases before the sun itself. The mystery is not what the ocean is made of. The mystery is how all of it, gathered together in one place, becomes a force no unprotected body has ever felt and lived to describe. Picture yourself sinking through open water, feet first, arms loose at your sides. At the surface, your body already carries a small weight of pressure, so small you never notice it. That is 1 atmosphere, the push of air above you. Go down just 10 meters, about the depth of a backyard pool stacked 3 times over, and the water alone doubles that weight. Your body would feel the change first in your ears, a dull ache as the air inside them tries to match the water outside. The force that does this work is simple to name and hard to picture. Water is heavy. Each layer of it presses down on the layer below, and that layer presses down on the next, all the way to the bottom. Add up 11 kilometers of that stacking weight. The distance a cruising airplane flies above the sea turned upside down, and you get a number that sounds almost calm when spoken aloud. 11,000 times the pressure of the air around you right now. The number is easy to say. What it does to a body is much harder to hold in the mind. One way to think about it involves the air pockets already inside you. Your lungs, your sinuses, the small hollow spaces behind your ears all hold air at surface pressure. As you descend, the water pressing on you does not ask your body to make room. It simply takes the room away. Air compresses. Space that once held a breath shrinks to a fraction of itself. Divers feel the beginning of this within the first few meters. A pressure behind the eyes, a tightness in the chest that has nothing to do with fear. Some researchers describe this force as acting evenly, the same way water pressure pushes equally from every direction at once. That evenness is part of why the deep ocean does not simply crush things the way a hand might crush a can. Instead, it presses in from all sides together, a whole body squeeze rather than a single blow, a shape that can equalize, that can let its inner pressure rise to match the outer pressure, can survive remarkably far down. A shape that cannot, one with rigid open spaces like human lungs or a submarine hull, faces a very different fate. This is where theories about the descent begin to diverge. One view holds that the danger builds gradually, a slow negotiation between inside and outside pressure that the body loses more and more of as it sinks. Under this idea, a diver without protection might survive briefly to modest depths before the imbalance becomes impossible to bear. Another view focuses less on gradual loss and more on threshold points, depths at which certain tissues or air spaces fail all at once, rather than slowly. Researchers who study diving physiology still debate exactly how these thresholds interact. Since bodies vary and conditions in real accidents are hard to study directly, what remains agreed upon is the direction of travel. Every meter down adds weight that never lightens, never pauses, never offers a breath of relief. If you continued down past the point where light fades, the pressure would keep rising in that same steady way. Indifferent to the dark, there is no dramatic jump at any single depth, no line in the water marking danger from safety. The crush simply accumulates, kilometer after kilometer, until by the time you reach the trench floor, 11 kilometers below where you started, the force pressing on your body would be measured in tons per square inch, rather than simple atmospheres. Engineers who build deep-sea submersibles speak of this pressure the way others speak of gravity, as a constant they design around, rather than a hazard they hope to avoid. Temperature plays its own quiet role in this story, though a smaller one. The deep ocean grows cold. As it grows dark, settling near freezing long before the trench floor. Cold slows chemical reactions, slows the body's responses, though pressure remains the dominant force shaping what can and cannot exist at these depths. Some scientists wonder whether cold and pressure together create conditions stranger than either could alone, a combination not fully mapped even now. Others argue temperature is a secondary detail beside the sheer mechanical weight of the water. If you stood at the surface and simply pictured the column of water above the trench floor, all 11 kilometers of it stacked invisibly overhead, your own shoulders might feel heavier just from the thought. That felt weight is imagination only. The true weight waits far below, patient and unmeasured by any human nerve, still shaping a place no unprotected body has ever touched and returned to describe. Picture your own lungs, right now, As you settle into the sheets, there is air moving gently in and out of them. There is air in your sinuses, air behind your eardrums, tiny pockets of gas tucked into the soft tissue of your gut. You do not think about these pockets. They are simply part of being a body that breathes. But if you carried that same body down into the Mariana Trench, those quiet pockets of air would become the first part of you to answer for the depth. At the surface, the air inside you sits at about 1 atmosphere of pressure. The same gentle push the whole ocean of air above your head exerts on your skin all day without you noticing. Every 10 meters of seawater you descend adds another full atmosphere on top of that. By the time a diver reaches 40 meters down, a depth many recreational divers visit on a single breath of caution and training, the pressure has already quadrupled. Now stretch that math down 11 kilometers, nearly 7 miles, to the floor of the trench. The number that waits there is not 4 atmospheres. It is not 40. It is roughly 1100 atmospheres, which people usually round, almost apologetically, to 11,000 times the pressure you feel lying in your bed tonight. It helps to make the number physical instead of just numerical. Imagine balancing a small car on every square inch of your skin, not one car for your whole body, one car for each single inch. That is close to what 1100 atmospheres actually means in force. Your body is covered in thousands of these inches. The weight is not sitting on you like a blanket. It is pressing in from every direction at once, evenly, the way water always presses, filling every curve and hollow with equal force. This is where the air pockets matter. Gas compresses far more easily than a liquid or a solid. Your blood, your muscle, your bone are made mostly of water and dense tissue, and water resists being squeezed. But the air in your lungs, sinuses, and inner ear behaves very differently under that same pressure. As you sank, long before you ever reached the bottom, those air spaces would shrink, collapsing toward a fraction of their surface size. Some researchers who studied diving physiology described this collapse as almost orderly, a physics problem playing out exactly as the equations predict. Others point out that the human body was never tested at these depths in any survivable way, so the finer details of exactly how tissue and air pockets behave together at the extreme end remain something we infer, rather than something we have watched happen and measured directly. Think about a plastic water bottle, empty, with the cap screwed on tight, carried down by a submersible. Photographs from deep dives show these bottles crushed into small, wrinkled lumps, sometimes barely larger than a fist, by the time they reach the bottom and return to the surface. The plastic did not break. It simply had nowhere else to go once the air trapped inside gave way to the water pressing in. A human chest, of course, is not a sealed bottle. It is a soft, complicated structure full of air spaces that would try to do the same thing, collapsing inward long before drowning ever became the relevant danger. There is another way to feel the scale of this number, one that has nothing to do with bottles or bodies. If you stood at the surface and dropped a steel ball, it would take more than an hour to sink all the way to the trench floor, falling steadily through darkening water the entire time. Commercial airliners cruise at roughly the same distance above the ground, 11 kilometers, that the Challenger Deep sits below the waves. If you have ever looked down from a plane window at clouds far beneath you, that same span of empty sky, turned upside down and filled with black water, is the space we are talking about. None of this tells us, with full certainty, exactly what the final moment would feel like, because no one has ever survived long enough at that depth to describe it, and researchers are left reconstructing the process from smaller pressures, animal studies, and physics rather than direct human testimony. The open question is not whether the pressure is real. It clearly is. The open question is what, precisely, happens in the space between the first air pocket giving way and the moment a body stops behaving like a body at all. If you tried to imagine standing on that seafloor yourself, your chest would already have folded inward long before your feet ever touched the sediment. Picture yourself floating just above the surface of the open ocean. Somewhere over the Mariana Trench, nothing marks this spot as special. The water looks the same as it does anywhere else, blue, moving gently, catching the light in soft ripples. There is no sign posted, no shift in color, no swirl to warn you that beneath your body lies 11 kilometers of water. If you dropped a stone here, it would fall for more than an hour before it touched anything solid. The first 100 meters would feel familiar to your skin. Sunlight would still reach you here, filtered and soft, the way it does in a shallow lake. Small fish would move past in loose groups, their scales flashing silver when they caught the light. This is the layer most people picture when they think of the sea. It is warm near the top and slowly cools as you sink, and it holds almost all the ocean life most of us will ever see with our own eyes. But this bright layer is thin. It reaches down only a few 100 meters before the light begins to fade, and by 1,000 meters it is gone completely. Below that line, the ocean holds a kind of dark that does not exist on land, not even at midnight, not even in a closed room. On land, some tiny amount of light usually finds its way in the deep ocean. Past a certain point, there is none, not dim light, no light at all. Your body would notice the cold before it noticed the dark. Near the surface, water might feel almost pleasant, especially in the tropics, but temperature drops fast once you leave the sunlit layer behind. By 1,000 meters, the water often sits just above freezing, and it stays that way for the rest of the way down. The cold at the bottom of the Mariana Trench is not much different from the cold at 1,000 meters. Once you leave the warm skin of the ocean, the deep sea settles into one long, steady chill that barely changes for kilometers. This raises a question that still puzzles researchers who study the deep ocean. The surface layer, warmed by the sun, is full of motion and life we can watch and measure. The layer below it, called the deep sea, covers most of the planet and yet remains largely unmapped in any real detail. Some estimates suggest we have explored less than a quarter of the ocean floor with any precision. The rest sits in this same permanent cold and permanent dark, largely unseen by any human eye. One idea about why so much stays unexplored points simply to cost and difficulty. Building anything that can survive the pressure at extreme depth and can carry cameras or people safely back up again is expensive and technically hard. A competing idea suggests the deep ocean has simply never captured public attention the way space exploration has, so funding and public interest lean toward the sky instead of the seafloor. Both explanations likely play some part, and researchers do not fully agree on which matters more. If you could hover in a research submersible at 2,000 meters, your porthole would show you nothing at all without the sub's own lights. Turn those lights on, and you might catch a glimpse of falling particles drifting past the glass, slow and constant, like snow falling upward and sideways at once. This is often called marine snow, and it is made of tiny bits of dead organisms and waste sinking from the layers above. It falls for days to reach the bottom, feeding creatures far below that never see the sun. The cold here is not dramatic. It does not bite or sting the way Arctic air does. It is simply constant, patient, and total. Your body, if unprotected, would lose heat quickly in water this cold, faster than in air of the same temperature, because water pulls heat away far more efficiently, long before pressure became the main danger. Cold alone would become a serious problem. Below this steady chill, the trench continues to drop, kilometer after kilometer, still dark, still cold, still largely unmeasured in detail. Researchers know the temperature holds close to freezing most of the way down, and they know rough shapes of the trench floor from sonar mapping done from ships far above. But direct visits remain rare, brief and difficult. What waits at true depth, beyond what most instruments have measured closely, remains an open question with only partial answers so far. If you floated here long enough, staring into the dark, you would begin to sense how much of this planet still keeps its secrets close. If you strapped on a mask and fins and swam down into open water, your body would start sending you warnings long before anything dangerous happened. At about 10 meters down, the pressure has already doubled from what you feel on the surface. Your ears would ache, your chest would feel a gentle squeeze, like a hand pressing softly on your ribs. This is your body's early warning system, and it works well for a while. Trained free divers, the ones who descend on a single breath with no tanks at all, can reach depths that seem impossible. Some have gone past 200 meters, holding their breath for minutes at a time. Their hearts slow down. Their spleens, of all things, contract and release a rush of oxygen-rich blood, an adaptation shared with diving seals. Nobody fully understands why the human body does this, though one theory suggests it is a leftover trait from some ancient aquatic ancestor. A competing view holds that it is simply a general mammalian dive reflex, not evidence of any watery past at all. The question of where this reflex comes from remains genuinely open, but even the best free divers turn back long before they reach anything like the crushing dark of the deep trenches. At roughly 250 meters, the pressure is about 26 times what you feel standing on a beach. Past this point, something called nitrogen narcosis begins to cloud the mind of a diver breathing compressed air. It feels, divers report, like a strange drunkenness. Judgment fades. Time seems to stretch and blur. If you were breathing ordinary air at that depth, you might feel a giddy calm settle over you, right as your situation grew most dangerous. Scuba divers, using standard equipment, rarely go past 40 meters. For this reason, technical divers with special gas mixtures can push further, sometimes past 100 meters. But every meter beyond that becomes a careful negotiation with the body's own chemistry. The gas is dissolved differently into blood and tissue as pressure rises. Nitrogen, mostly inert and harmless at the surface, becomes something closer to a slow poison of the mind at depth. Oxygen itself, the very gas that keeps us alive, turns toxic under enough pressure, triggering seizures in a process called oxygen toxicity. This is the strange truth about turning back. It is rarely the water itself that stops a diver. It is the air they carry with them, transformed by pressure into something the body cannot process. Even with the most advanced gas blends and the most careful training, human divers using self-contained breathing systems have only reached around 300 meters. That is a remarkable achievement, and also a small fraction, less than 3%, of the total depth waiting at the bottom of the Mariana Trench. If you descended past this point in ordinary scuba gear, your body would begin to fail in ways no amount of training could fix. The gas mixtures that keep you alive at shallow depths become the very thing that kills you further down. This is one of the quiet ironies of the deep ocean. The barrier is not really about water pressure crushing your bones. Not yet. Not at these depths. It is about the chemistry of breathing itself breaking down. Some researchers wonder whether future gas mixtures or entirely different breathing technologies might push the limit further still. Others believe the human body has essentially reached its natural ceiling, and that any depth much beyond 300 or 400 meters will always require a rigid suit or a submersible hull to survive. Both possibilities remain on the table. Nobody has proven which one is correct. What is certain is this: somewhere around 300 to 400 meters, the ocean draws a line that no unprotected human body has crossed and returned from safely. Below, that line lies over 10 more kilometers of water, cold and lightless, pressing down with a weight most of us will never feel directly. Free divers, technical divers, the most careful and well-trained people in the world, all turn back here. If you found yourself at this depth without protection, your mind would likely feel calm, even as your body faced real danger, and that calm would be the most dangerous part of all. The ocean does not announce its limits with alarm. It simply waits, patient and indifferent, for the moment your body's own signals stop making sense. If you rose too fast from a deep dive, your blood would begin to fizz. That is not a figure of speech. Nitrogen gas, pressed into your blood and tissues under the weight of the water above, would come out of solution the way soda does when you twist off a cap. Divers call this the bends, and it follows a rhythm as old as human diving itself. Go down, absorb gas, come up slowly, or suffer for the mistake. Pattern is a cycle, because the ocean does not forgive shortcuts. A diver who descends to 30 meters and stays too long must ascend in careful stages, pausing at set depths to let the nitrogen leave the body gradually. Skip a stage, and bubbles form in the joints, the spinal cord, sometimes the brain. Your knees would ache first, then your judgment would go soft, like a fog rolling into a clear room. This is why divers speak of the deep in stages, in slow returns, never in straight lines up. The rhythm extends further than the bends alone. Nitrogen narcosis follows its own cycle, one tied directly to depth rather than time. Past about 30 meters, nitrogen begins to act on the brain almost like a mild intoxicant. Divers have reported calm, even euphoric confusion at depth, followed by a return to clear thinking once they rise. Some researchers compare it to the effect of drinking, gone, as soon as the pressure lessens. The exact mechanism is still debated. One theory holds that nitrogen dissolves into the fatty membranes of nerve cells and slows their signals. Competing viewpoints to broader changes in brain chemistry under pressure, not tied to any single gas. Neither explanation has fully closed the question. Then there is oxygen itself, usually life's most reliable gift. Turning strange under enough pressure, breathe ordinary air past about 60 meters, and oxygen toxicity can set in, causing convulsions with little warning. The molecule that keeps you alive at the surface becomes something your body cannot tolerate in excess below it. This is why deep divers switch to blended gases, thinning the oxygen and nitrogen with helium, trading one set of risks for another. Helium brings its own cycle of problems, including tremors and disrupted sleep on very deep, very long dives. There is no gas mixture that removes the danger. There is only a shifting balance of which danger you choose to face. If you were descending through these zones, your body would move through a series of quiet private crises, one gas at a time, each with its own depth, its own warning signs, its own slow unwinding on the way back up. The Mariana Trench sits far beyond any of this. No blend of breathing gas changes the outcome down there. The pressure alone, 11,000 times that of the surface, would compress and stop a human body long before any narcosis or gas sickness could matter. The trench does not follow the cycles that a scuba diver learns to respect. It exists, past the edge of every known warning sign, a place where the rhythms of survivable diving simply do not apply anymore. Yet the ocean's own cycles continue there, indifferent to human limits. Sediment falls in a slow, endless rain, a process some scientists call marine snow, drifting down for days from the surface to the floor. Whale calls pulse through the deep water in patterns that repeat across seasons. Currents shift with the turning of the planet and the pull of the moon, moving water in slow loops that take centuries to complete a single circuit. These rhythms do not pause for our absence. They do not know that no person has stood among them and lived to describe it firsthand. Some researchers wonder whether the deep sea holds cycles we have not yet named, patterns of pressure and temperature and chemistry that repeat over spans longer than a human life, or longer than recorded history. Others argue that, without direct, sustained observation at full trench depth, such ideas remain guesses dressed as theory. The question of what regular rhythms might exist down there, beyond tides and falling sediment, is still open. If your body could somehow tolerate the pressure and travel down through every zone, you would pass through the bends, then narcosis, then oxygen's strange betrayal, one by one, like doors closing behind you. Past the last door, there would be only the pressure itself, patient and total, with no cycle left to explain, and no stage of ascent slow enough to undo what had already happened. The warnings the body gives at shallower depths simply have nothing left to warn about once you have gone that far down. Picture yourself standing at the rail of a research ship, looking down at calm grey water that gives away nothing about what lies beneath it. Somewhere far below, a machine is descending on your behalf, carrying cameras and lights into a place your body could never visit and return from. You feel the deck gently roll under your feet. The machine feels nothing at all, at least not in any way you would recognize. These machines come in a few different shapes, built by different teams with different ideas about how to solve the same problem. Some are called ROVs, remotely operated vehicles, tethered to the ship above by a long cable that carries power down and video signals back up. Others are autonomous, moving on their own through the dark, following a program instead of a human hand. Still others are crude submersibles, carrying 1 or 2 or 3 people inside a thick sphere of titanium, built to survive the very pressure that would end you in an instant. The engineering problem is the same one your body faces, just solved with different materials. A human chest cannot resist 11,000 times the pressure of air at the surface. Steel and titanium can, if shaped correctly, usually as a sphere, because a sphere spreads force evenly across its whole surface with no weak corners. Inside that sphere, the air stays at roughly the same pressure you feel right now, sitting still, breathing normally. Outside it, the ocean is pressing in with a force that would flatten almost anything else. One theory about why we have sent so few crude submersibles to the deepest trenches is simply cost and risk. Building a vessel that can survive that pressure and bring people home again takes years and enormous resources, and the margin for error is thin. A competing view holds that the bigger obstacle is not money but purpose. Unmanned vehicles can carry cameras, sensors, and sampling arms without risking a human life, and they can stay down far longer than a person could comfortably endure. Both views agree on one thing: crude dives to the deepest trenches remain rare events, not routine science. The tether itself carries its own quiet mystery. A cable, several miles long, thin as a garden hose in places, has to survive the crushing pressure at depth while still carrying electricity and data without failure. Engineers have spent decades refining the materials and the insulation. And even now, a tangled or severed line can end a mission instantly, leaving a vehicle stranded on the bottom in permanent dark. If you held that cable in your hands on deck, it would feel unremarkable, almost soft. Miles below, it is doing something almost nobody fully understands how to picture. Autonomous vehicles avoid the tether problem entirely, but they trade it for another kind of uncertainty. Once released, they follow their programmed path without a live human hand guiding them, communicating only in short bursts through sound waves, since radio signals do not travel through seawater. If something goes wrong at that depth, there is often no way to know until the vehicle fails to surface at its planned time. The ocean simply keeps its secrets a little longer. What these machines have found, piece by piece, is a picture of the trench floor that no eye had ever seen directly before their cameras arrived. Soft sediment, pale in the artificial light, undisturbed except for the slow crawl of small animals across its surface. Debris that fell from far above, settling there over spans of time that stretch past ordinary imagination. The machines do not feel awe when they see this. They simply record it, frame after frame, and send it home to people who do feel awe, sitting at monitors thousands of miles away. The question of how close these vehicles bring us to truly understanding the deep remains open. Some researchers argue that a camera and a robotic arm can gather nearly everything a human presence could, without the risk. Others feel that something is still missing when no person is physically there to notice the small, unexpected thing that a program was never told to look for. Both sides agree the sample size is still tiny. Only a handful of vehicles have ever reached the deepest trenches at all, and each dive is treated as a rare and costly event rather than a routine visit. If you could ride inside one of these machines, descending slowly through the dark for hours, the cold would settle into the hull around you long before you reached the bottom. The lights outside would show you nothing until they were switched on, and then only a small circle of grey-brown floor, waiting exactly where it had waited for longer than you can easily hold in your mind. Picture standing at the edge of a map, looking at a blue so dark it seems almost black. Somewhere below that surface Folded into the floor of the Western Pacific lies a scar in the crust, deeper than any mountain on land is tall. Your body, standing on that imagined summit at the bottom, would feel a weight almost impossible to hold in the mind. The trench runs for about 1,500 miles, a long crescent-shaped gash near the island of Guam, formed where one great slab of ocean crust bends downward and slides beneath another. Its deepest known point, called the Challenger Deep, drops nearly 11 kilometers below the surface. That is close to the cruising height of a passenger jet, except turned upside down and filled entirely with water, darkness, and cold. If you dropped a steel ball from the surface, it would fall for over an hour before it touched bottom. At that depth, the pressure is often described in a single number. About 11,000 times what you feel standing in open air right now. Numbers like that are easy to say and hard to actually picture. One way scientists try to make it real is by comparison. The pressure at the bottom of the Challenger Deep is roughly like having 50 jumbo jets stacked on top of your chest, their combined weight pressing evenly across every inch of your skin. Your body could not translate that into pain, the way a bruise or a break would feel. It would simply be crushed everywhere, all at once, before pain had time to register. This is what makes the trench different from almost every other extreme place on Earth. A mountaintop can kill you slowly, through cold or thin air. A desert can kill you slowly, through heat and thirst. The Challenger Deep offers no slow version. There is no adjustment period, no gradual decline. There is only the line where survivable pressure ends and unsurvivable pressure begins, and that line sits far above the actual floor. Only a handful of piloted trips have ever reached the very bottom. The first came in 1960 in a steel submersible with walls thick enough to hold back that pressure, carrying 2 men down for a matter of hours. Decades passed before anyone returned. Even now, most exploration of the deepest trenches on Earth is done by unmanned vehicles sent down alone, because building something a person can survive inside is still one of engineering's harder problems. Some researchers wonder whether we will ever send many humans there at all, given the cost and risk involved. Others believe better materials and smaller, tougher vessels will make repeat visits more common within a few decades. Both views remain open, because so few trips exist to compare. What makes the trench stranger still is that it is not empty. Sediment drifts down from the surface for millions of years, settling into a soft, undisturbed floor, unlike almost anywhere else on the planet. Small sea cucumbers move across that sediment. Certain fish species, pale and slow, have been recorded living at depths once thought impossible for anything with a spine. If you tried to bring one to the surface too quickly, its body would not survive the change, because it is built around living inside that pressure, not around resisting it. The heat down there is nothing like a volcano, despite the trench forming from grinding tectonic plates. Temperatures near the bottom hover just above freezing cold, enough that your body would lose warmth quickly, even before pressure became the larger problem. Combine that cold with total darkness, since no sunlight reaches anywhere near that depth, and you get an environment closer to another world than to any ocean shoreline you have stood on. The open question researchers keep circling back to is simple to ask and hard to answer. We understand the physics of pressure well enough to build a hull that survives it. We do not yet fully understand how so many creatures thrive in a place with almost no light, extreme cold, and force enough to crush steel improperly designed. Some think the answers lie in slow-moving proteins and unusual cell structures. Others think we have barely sampled enough of the trench to know what we are even looking at. If you could stand, impossibly, on that distant floor, the weight above you would settle without sound, without warning, and without any signal that anything unusual was happening at all. If you could somehow drift down to the trench floor and shine a light on the sediment, you might see something move. Not away from you in fear, just moving slowly, the way life moves when it has never needed to hurry. Down there, in the deepest parts of the ocean, small creatures live out their whole lives under pressure that would crush your chest in an instant. They are not surviving the pressure. They are built by it, shaped around it, made of a body plan that has never known anything else. A snailfish pulled up from the Mariana Trench looks almost too delicate to be real. Its body is soft and pale, almost see-through, with a skull that is thin and loosely built compared to fish that live near the surface. For a long time, researchers assumed nothing with a backbone could live much past 7 or 8 kilometers down. Then cameras and traps kept finding these small, pale fish resting comfortably far below that line, in trenches around the Pacific. Their bodies seemed to work by matching the pressure outside with a similar pressure inside, so that nothing is pushed or squeezed unevenly. It is less like armor and more like agreement. The water outside presses in, and the fish's own tissues press back with equal quiet force. One idea researchers point to involves a small chemical compound called TMAO, short for trimethylamine N-oxide. In these deep fish, it seems to help proteins keep their shape under pressure that would otherwise bend them out of shape and stop them from working. The deeper the fish lives, the more of this compound its tissues seem to carry. Some scientists have proposed there may be a natural limit to how much of it a body can hold, which could explain why almost nothing with a backbone lives much past around 8.5 kilometers down. Other researchers are more cautious, noting that trenches are so hard to sample that the true lower limit for fish life is still not settled. It remains an open question, one measured a few rare specimens at a time. Without a backbone, though, life seems to go deeper still. At the very bottom of the Mariana Trench, in the near-freezing dark, researchers have found tiny amoebas called xenophyrophores, along with worms, small shrimp-like creatures, and sea cucumbers moving across the soft sediment. Your body, at that same depth, would already be beyond any hope of intact function. These animals do not fight the pressure. Their soft, simple structures seem to have little empty space inside them for the water to crush. No lungs, no large air-filled cavities, nothing for 11,000 times the pressure of open air to collapse. That absence of empty space may be the real quiet secret of the deep sea. Pressure is dangerous mostly when it meets a pocket of gas, something soft and hollow that can be squeezed down to nothing. A body full of air, like yours, is full of exactly that kind of danger at depth. A body that is mostly water and dense tissue, like a deep sea worm's, has far less to lose. Some researchers think this single difference explains more about who can live down there than any special deep-sea toughness. Other researchers point out that biochemistry, not just body shape, clearly plays its own separate role, and that both ideas are probably part of the same larger answer. If you brought one of these creatures to the surface, it would not thank you for the light or the warmth. Many die during the trip up. Their proteins and membranes, built for one pressure, suddenly asked to work in another. A few unusual species have been kept alive briefly in pressurized chambers built to mimic their home depth, but it takes careful engineering just to keep a small worm comfortable for a few hours outside the trench. The mismatch runs in both directions. Your body cannot go down to them. Their bodies, mostly, cannot come up to you. What stays unresolved is how many more of these creatures are still waiting in the dark, unseen and undescribed. Trench floors have been sampled in only a scattering of places. Small patches of mud, lit briefly by a passing submersible's lamp, before the dark closes back in. Each new expedition tends to find species that had never been recorded before, sitting quietly in sediment that took millions of years to settle. If you stood at the edge of that trench floor in a body built for open air, none of this quiet toughness would help you. The pressure would meet you the same way it meets everything else down there, evenly, calmly, without malice. It would simply be too much for a body made for shallow water to hold. Picture yourself on the deck of a wooden ship in the 1870s, holding a coil of rope with a weight tied to its end. That was the beginning of deep-sea science. Sailors on the HMS Challenger, a British research ship, spent years lowering weighted lines into the ocean, waiting for the rope to go slack, and counting how many feet had disappeared into the dark. It was slow work. It was also the only way anyone had to answer a simple question: how deep does the ocean actually go? The Challenger expedition found something startling near the Mariana Islands in 1875. Their rope kept falling, foot after foot, hour after hour. The line paid out into water that seemed to have no bottom at all. When it finally stopped, they had measured a depth of more than 8,000 meters. No one on board fully understood what they had found. They only knew their instruments, simple as they were, had touched something far larger than expected. If you had stood on that deck, you would have felt the rope hum faintly in your hands. Tugged by currents you could not see, you would have watched hour after hour pass with no answer. Just rope sliding into black water. That patience, more than any tool, was the real instrument of early ocean science. Decades later, sonar changed everything. Ships could send sound pulses downward and listen for the echo bouncing back. The time it took the echo to return told them the depth, calculated from the known speed of sound in water. This method, called echo sounding, was faster and far more precise than rope and weight. It let scientists map the trench properly for the first time, revealing a valley cut into the ocean floor, far deeper than anyone's rope had ever reliably confirmed. Sonar also revealed something stranger than depth. As ships pinged sound into the water, they picked up echoes from mid-depth layers that seemed to rise and fall with the sun. For a time, some crews wondered if they had found a false sea floor, a solid layer no one had mapped before. It turned out to be something else entirely, though. The full picture would take years to piece together. That layer was a moving mass of small fish, shrimp, and other creatures so dense that sound bounced off it as if it was solid ground. During the day, this layer sinks into deeper water, avoiding the light. At night, it rises toward the surface to feed. This nightly rise, still not completely understood in all its details, is now believed to be the largest daily movement of animal life on the planet, larger than any migration on land. The chemistry of the deep held its own puzzles. Early scientists assumed the deep ocean would be a chemical desert, too cold and too dark to sustain much life. Water samples brought up from the depths seemed to support this. They contained few nutrients near the surface layers scientists first tested, but later sampling, done more carefully and at greater depths, revealed something different. Deep water holds dissolved minerals, gases, and organic material falling slowly from above, a chemistry all its own, shaped by pressure instead of sunlight. One long-standing debate concerned whether life could exist at the bottom of the trench at all. Some researchers in the early 20th century assumed the pressure alone would prevent anything larger than bacteria from surviving. Others pointed to occasional strange catches in deep trawl nets, oddly shaped fish, and worms no one could explain. The disagreement lasted for decades, unresolved by any single expedition, because so few instruments could survive the descent long enough to check. If you had been the one hauling in one of those early trawl nets, you might have found something pale and strange caught in the mesh, its body already collapsing under the sudden change in pressure. You would not have known, holding it in your hands, whether you were looking at a rare accident or a normal resident of a world you could not otherwise visit. The mystery those sailors and scientists faced was never really about depth alone. It was about how little their instruments could tell them, and how much they had to infer from small clues pulled up from a place none of them could see directly. Every method, from rope to sonar to sample bottles, gave a partial answer, and each new answer opened new questions about pressure, darkness, and chemistry in equal measure. Even now, deep sea chemistry remains only partly mapped. Some pockets of the trench show mineral concentrations that surprise researchers each time new sampling gear reaches the bottom. Whether these pockets are common or rare across the wider trench floor is still an open question, one that continues to draw new instruments downward, following the same dark path that rope and weight first traced more than a century ago. If you sank into the trench, you would lose your sight long before you lost anything else. Past 1,000 meters, no sunlight reaches down at all, but your ears, if you could somehow keep listening, would find the opposite is true. Sound does not fade in the deep ocean. In many ways, it travels better there than it does near the surface. This seems backward. Light disappears within the first few hundred meters, swallowed by water molecules that scatter and absorb it, one wavelength at a time. Red goes first, then orange, then yellow, until only a deep, aching blue remains, and then nothing. You would expect sound to behave the same way, fading as the water thickens and the pressure builds. Instead, sound waves move faster and farther as they descend, carried by a strange corridor of cold, dense water that acts almost like a tunnel. Scientists call this the deep sound channel, sometimes named for the researchers who first mapped it in the 1940s. At a certain depth, usually somewhere near 1,000 meters, temperature and pressure combine in a way that lets sound waves travel with almost no loss of energy. A whale call or a seismic rumble entering this channel can travel for thousands of kilometers, bouncing gently within the layer instead of scattering upward or downward. Some low-frequency sounds made by blue whales have been tracked crossing entire ocean basins, heard by listening stations on the far side of the world. Your body, at the bottom of the trench, would sit inside a world built for sound the way the surface world is built for light. This means the deep ocean is not the silent place many people imagine. Distant ship engines hum through it. The groan of shifting seafloor rock travels through it. Whale calls move through the dark for hundreds of kilometers, arriving faint but intact. Researchers, listening with underwater microphones, called hydrophones, have picked up sounds whose source they still cannot explain, low rhythmic pulses that do not match any known animal or machine. One theory holds, that some of these are simply whale calls, distorted by long travel through cold water layers. Another theory suggests some may come from ice movement or geological activity far from where the microphone sits. Both explanations remain open, and the recordings are filed away as unresolved. If you stood on the ocean floor at the bottom of the trench, sound would reach you from places light never could. A groan from a fault line 100 kilometers away might arrive as a low vibration under your feet, felt more than heard. The calls of animals living far above you, near the edges of sunlight, could theoretically travel down and across this channel, though very little of that sound would make it all the way to 11 kilometers. Researchers still debate how much energy survives that final plunge into the trench, where pressure is highest and the channel's usual rules begin to change. There is a puzzle inside this puzzle. Pressure changes the density of water, and density changes how fast sound moves through it. Near the surface, sound travels around 1,500 meters per second. Near the bottom of the deepest trenches, that speed shifts again, shaped by the extraordinary pressure pressing down from 11 kilometers of ocean above. Exactly how sound behaves at those final depths, in that narrow slice of ocean humans have almost never reached, is still not fully mapped. The few instruments lowered down there recorded fragments, not a full picture. Some researchers wonder whether entire communication systems exist among trench life, using sound in ways adapted to complete darkness. If sight is useless in the black water, sound and vibration might carry more meaning to the creatures living there than color or shape ever could. Other researchers caution against assuming too much, since so few recordings exist from that depth and so few animals have been studied in place. The honest answer is that no one yet knows how much of the trenches world is built on sound, and how much silence still waits undiscovered. Your body, wrapped in a pressure hull and lowered into that channel, would feel none of this directly, but the water around you would be alive with movement your ears could never catch, unaided. A quiet, invisible traffic of vibration, crossing an ocean whose depths remain, in this one way, easier to hear than to see. Picture yourself inside a small steel sphere, no wider than a car, dropping through black water for hours. Your knees would touch the wall in front of you. Your breath would sound loud in the quiet, the only sound besides the soft hum of life support. This is what it takes to send a human body toward the bottom of the Mariana Trench, 11 kilometers down, where the pressure reaches over 1,000 times what you feel at sea level. No person can go there unprotected. So instead, we build a shell strong enough to argue with the ocean, and we climb inside it. The first machines built for this kind of depth were simple by comparison. In 1960, a vessel called the Trieste carried 2 men to the trench floor, its cabin a thick sphere of steel, welded to a large float, filled with gasoline, which is lighter than water, and helped it rise back up. The design worked, but barely. The engineers of that time were working at the edge of what metal could hold. One window on that dive reportedly cracked under the strain, a detail still discussed and debated by historians of ocean engineering today. The mission succeeded. The margin for error, by modern standards, was thin. Since then, submersible design has changed the shape of the problem more than the size of it. Modern deep diving vessels use spheres made of titanium or thick acrylic, materials chosen because a sphere spreads pressure evenly across every point of its surface. There are no flat panels down there, no sharp corners. Pressure does not tolerate weak points, and a flat surface gives it somewhere to push. Engineers describe the ideal deep submersible almost like a soap bubble. A perfect curve with no direction of the ocean is stronger than steel that is shaped wrong for the job. Your body, inside that sphere, would feel almost nothing unusual for most of the descent. The air inside stays at normal pressure, the same pressure you feel right now reading this. That is the strange part of submersible design. The machine takes on the full crushing weight, so the person inside does not have to. If you looked out the window during the dive, you would see the water outside pressing against thick acrylic or glass, sometimes flexing slightly under strain, while the air around your own skin stayed calm and unbothered. The mismatch between what your body feels and what the machine is enduring is part of why this kind of travel unsettles even trained pilots. Engineers still debate the best way to build these vessels. Some favor thick metal spheres, trusted for their long history and predictable behavior under stress. Others favor acrylic, prized because it lets a pilot see the deep water directly, though it must be built with wide margins of safety, since cracks in acrylic can be harder to detect early. Neither approach has fully replaced the other. Both remain in active use today, a sign that the question of the safest shape for surviving crushing depth is still open, still argued over in engineering papers and design reviews. The loss of the submersible Titan in 2023, while diving toward the wreck of the Titanic, is often mentioned in these discussions, and it deserves to be spoken of gently. The investigation into what happened is still being studied by engineers and safety officials, and many of the exact causes remain under review. What is agreed upon by most in the field is that the pressure at those depths leaves almost no room for material fatigue or design shortcuts. A single flaw, invisible on the surface, can become the whole story once the water outside reaches thousands of times atmospheric pressure. That event reminded many people, quietly and without spectacle, that the ocean does not forgive uncertainty the way the open air sometimes can. Elsewhere in engineering, we see echoes of the same problem. Airplanes pressurize their cabins to keep passengers comfortable at high altitude, using the same basic idea of controlled contrast between inside and outside. Spacecraft do something similar in reverse, holding pressure in against the near vacuum of space. The ocean depths ask engineers to solve the mirror version of that puzzle, holding pressure out instead of in. If you have ever felt your ears change on a plane, you have felt a small cousin of the force these submersibles are built to resist, magnified many thousands of times over. No perfect design has emerged, no material has ended the argument. Each dive is still, in its own way, a controlled negotiation with a place that offers no negotiation back. The trench does not care what the sphere is made of. It only asks whether the math was right. If you rode down inside one of these vessels tonight, you would feel calm cabin air on your skin the entire way, even as 11 kilometers of ocean quietly tested every rivet and seam around you. Picture yourself sealed inside a steel sphere, sinking slowly toward the bottom of the Mariana Trench. You would feel almost nothing at first. The hull around you would be doing all the work, holding back a pressure that grows heavier with every meter you fall. Engineers have spent decades trying to picture what would happen if that hull ever failed at full depth. Not because it is likely. Modern pressure vessels are tested and retested, built with margins far beyond what the deep ocean demands. But the question still matters, because it tells us something about the size of the forces waiting down there. At 11,000 meters, the water pushes in with more than 16,000 pounds of force on every square inch. Your body, wrapped in nothing but skin and bone, could not resist that for even a moment. One idea, drawn from engineering studies and a small number of historical accidents in shallower water, describes the failure as fast. Faster than a nerve can carry a signal to the brain. If a viewing port or a weld gave way at full ocean depth, the inward rush of water would arrive before pain had any chance to register. Some engineers who study implosions call this a mercy of physics, though they are careful to say it is a mercy built from speed, not comfort. The body would not have time to know what was happening to it. Other researchers push back gently on how clean that picture really is. Deep sea implosions are hard to study directly because they are rare, and because the wreckage sits kilometers down in total darkness. Most of what we know comes from smaller scale tests, pressure chambers, and mathematical models, rather than direct observation of a human scale failure at 11 kilometers. The models agree on the extreme speed involved. They disagree or simply stay silent on some of the finer details of force and sequence. The honest answer is that no one has watched this happen and lived to describe it, and no instrument has ever captured the full event in complete detail. If you were inside a vessel like this, your body would still be moving through familiar experience, one instant, and gone from that experience entirely in the next, with nothing in between that your mind could process. That gap, the total absence of a felt transition, is part of why the deep ocean holds such a strange grip on the imagination. We tend to picture drowning when we think of deep water, a slow struggle for air, a fight that stretches out in time. But at these depths, the danger is not the water entering your lungs. It is the immediate and total collapse of the space your body occupies, driven by a weight equal to the ocean pressing down from 11 kilometers above. The trench itself does not change quickly. Its rocks and sediment shift over millions of years, nudged by the slow grind of tectonic plates sliding past one another. But our understanding of what happens to a human body there has changed a great deal, even in the last few decades. Early pressure research relied on animal studies and small mechanical models, offering only rough guesses about what extreme depth would do to living tissue. Better materials science, sharper computer modeling, and a handful of hard lessons from failed equipment have sharpened the picture since then. What remains constant is the trench itself, patient and dark, indifferent to how well we understand it. Some researchers wonder whether framing this as violence at all misses something. The water is not attacking anything. It is simply filling space the way it always does, the way it has for millions of years at the bottom of every ocean basin on Earth. The pressure is not a force aimed at a body. It is the ordinary state of that depth, and a human body is simply the unusual thing that arrives there uninvited, still shaped for the thin air and gentle weight of the surface world. If you could somehow survive to feel it, the last sensation before failure might not even register as fear. It might simply be a low groan of metal, a faint change in the air pressure inside the cabin, and then nothing at all to mark the difference between 1 second and the next. Whether that counts as painless or simply as unknowable remains an open question that instruments alone cannot answer. Down there, in the endless cold and the total dark, the ocean keeps doing what it has always done, patient and unbothered, while we continue building steel shells thin enough to carry us and strong enough, we hope, to bring us home. Your body, wrapped only in what it was born with, would never make it past the first few 100 meters of that same weight. If you sank slowly through the last 100 meters above the trench floor, you would already have spent hours in total darkness. No light from the sun reaches this far down, not dim light, not blue light, filtered and faint, none at all. The sun's photons stop penetrating seawater long before this depth, absorbed and scattered by hundreds of meters of water above, by 1,000 meters. Sunlight is already gone. The remaining 10 kilometers below that point exist in a darkness so complete that human eyes, adapted over millions of years to work with even faint starlight, register nothing. Not black in the way a closed room is black, black in the way that has no comparison on the surface of the earth at all. A small number of vehicles have carried people into this darkness and back. In 1960, a manned submersible reached the bottom of the Challenger Deep, the deepest known point in the Mariana Trench, carrying 2 men inside a steel sphere. In 2012, a solo dive reached the same depth again. In 2019, another expedition returned there, followed by several more dives in the years after. Each of these journeys took hours of descent through cold, pressing dark before reaching the sediment floor. Each pilot brought lights with them, because without an artificial source, there is nothing at all to see. The lights themselves reveal something strange about this place. A submersible's beam, cutting through trench water, does not illuminate a wide glowing space the way a flashlight does in a foggy field. It carves a narrow cone through water that seems to swallow the light at its edges. Sediment particles drift through the beam like slow snow, catching the glow for an instant before falling back into the dark. Some researchers describe it as looking into a blizzard, except the flakes are falling at a speed that took millions of years to build the layer waiting below. If you held a light source at that depth, you would notice it reveals almost nothing beyond a few meters. Whatever exists just past the edge of the beam remains unseen, not because it is hidden, but because darkness this total does not thin out gradually. It simply continues, unbroken, in every direction the light does not directly reach. Some of the creatures living at this depth make their own light. Bioluminescence, a soft glow produced by chemical reactions inside certain deep-sea organisms, flickers in patterns that scientists still do not fully understand. One theory holds that these small bursts of light serve as communication, a way to signal across a stretch of water where no other visual cue could ever travel. Another theory suggests the glow works as a lure, or a startle response meant to confuse a predator for the half-second needed to escape. Which explanation fits which creature, and whether some species use light for a purpose no one has identified yet, remains open. Researchers have only observed a small fraction of the organisms living at these depths, and many behaviors have never been filmed in their natural setting at all. The window of a submersible offers its own strange relationship with light. From inside the cabin, the pilot watches the beam pass through water that grows heavier with every meter of descent, though the light itself shows no sign of that pressure. Outside the thick viewport, 11,000 times the pressure of surface air presses inward on every surface. Inside, the light glows the same as it would in a calm harbor. The two realities sit only centimeters apart, separated by a pane engineered to hold that difference without failing. Engineers still debate the safest shapes and materials for these windows, since a floor invisible at the surface could behave very differently under that much force. You would feel, if you made this descent yourself, a kind of quiet that light cannot fill. The beam shows you the particles, the sediment, the occasional pale shape moving at the edge of visibility, but it does not shrink the darkness around it. It only borrows a small patch of the dark for a little while. Whether any large-scale features of the trench floor remain completely undocumented, simply because no light has ever reached them, is still an open question. Full darkness does not just hide details. It raises the question of how much of this place has been seen by anyone at all, human or machine, in the whole of its existence. Picture a suit of metal built to hold a shape against a force that wants to crush every shape into one flat nothing. If you tried to wear ordinary cloth or rubber at the bottom of the Mariana Trench, it would offer no more resistance than a whisper. Your body needs something else entirely, something closer to a small building than a garment. This is why the vessels made for that depth do not look like diving suits at all. They look like spheres. A sphere is the strongest shape against pressure that pushes in from every direction at once. Engineers did not choose it for beauty. They chose it because a sphere spreads force evenly across its whole surface, with no flat panel and no sharp corner to become a weak point. Think of an eggshell, thin and delicate in your hand, yet able to resist a surprising squeeze because the curve carries the load around instead of letting it collect in one place. The pressure chambers built for the deepest dives borrow that same old trick, scaled up in titanium and steel. Inside one of these spheres, a person sits curled in a space barely large enough to stretch their legs. The walls might be several inches of metal, cold to the touch even through gloves. If you sat inside, you would feel the hum of instruments and hear your own breathing grow strangely loud in the quiet outside that wall. At full depth, the pressure reaches over 16,000 pounds per square inch. Inside, the air stays close to what you would feel standing on a beach. The sphere's whole purpose is to hold that difference apart, second after second, for hours at a time. One theory among engineers is that thickness alone is not what saves the sphere. What matters more is the evenness of the curve, and any tiny flaw, a bubble in the metal, a seam poured wrong, becomes the place where the whole structure could fail first. This is why early pressure spheres were tested again and again, sometimes to destruction, in tanks built to mimic trench depth on the surface. Some researchers have wondered whether titanium, prized for its strength and lightweight, hides flaws that ordinary methods cannot detect until the metal is already deep in the water. Others argue that modern scamming has mostly solved that problem. The debate over how much margin for error is truly built into these hulls has never fully closed. The windows are their own separate puzzle. Glass seems like the wrong material for a wall that must hold back tons of water. And yet a specific kind of thick, cone-shaped acrylic window has proven remarkably capable of doing exactly that. As pressure rises during a descent, the window is squeezed into its frame more tightly, not less, so the crush of the ocean actually helps seal it rather than force it open. If you pressed your palm against that window near the bottom of the trench, you would feel it faintly warm from the friction of the material compressing, and utterly solid, without a trace of a groan or shift. And yet, pilots have reported sounds, not sounds from outside, since sound at that depth arrives through water and metal, not through empty space, but small, sharp cracks and pops from within the hull itself as it settles under the strain. One idea is that these are harmless, simply the metal or acrylic finding its resting shape under new pressure, the way a house creaks as it cools at night. A competing idea holds that any unexpected sound in a vessel built for such extremes deserves to be treated as a possible early warning, and that the difference between a harmless creak and a dangerous one is not always obvious in the moment. No engineer claims to have fully mapped every sound a pressure hull might make at extreme depth, because so few vessels have gone there enough times to build that record. If you were inside that sphere, on such a dive, hours into your slow fall, through total darkness, every distant tick or groan would arrive with unusual weight. You would know, somewhere in your body, that the shape around you is the only thing standing between the ordinary pressure of your own lungs and a force 11,000 times stronger. The sphere holds. It has held before, but each dive is still, in some sense, a new question asked of an old design, one that has not yet been asked enough times for anyone to call it fully answered. Picture yourself floating above a map of the Mariana Trench, drawn small enough to fit on a table. It would look like a thin scratch on the blue, barely worth a second glance. But that scratch holds numbers that are hard to hold in the mind, even when they are written down clearly and simply. The trench runs almost 7,000 kilometers along the floor of the Western Pacific. That is longer than the distance across the United States. Its deepest point, called the Challenger Deep, drops nearly 11 kilometers below the surface. If you could lay Mount Everest into that gap, its peak would still sit under more than 2 kilometers of water. Your body, standing at sea level, cannot picture 11 kilometers of downward space, but the math behind it is simple enough for anyone to follow. Pressure grows by about 1 atmosphere, the weight of the air pressing on you right now, for every 10 meters you sink into seawater. At 10 meters you feel 2 atmospheres. At 100 meters, 11. This ratio holds steady, almost like a rule of nature, keeping perfect time. By the time you reach the trench floor, the number climbs past 1,000 atmospheres. That means the water above you weighs on your body with a force 11,000 times what you feel breathing on dry land. The number is easy to write. What it would actually do to your chest, your ears, the air pockets in your sinuses, is much harder to picture, and that gap between the number and the feeling is part of why this place stays strange, even to people who study it for a living. Some researchers describe this pressure growth as elegant, almost musical, because it is so consistent. 10 meters, 1 atmosphere. 10 meters, 1 more. The ocean does not skip steps or bend the rule for anyone. A submersible descending towards the Challenger Deep can predict almost to the minute when it will cross each threshold, because the math holds firm the entire way down. There is a strange comfort in that. The trench is one of the most remote and hostile spaces on the planet, and yet the physics that governs it can be written on a single page. But numbers that behave neatly on paper do not always explain what happens to living tissue. And this is where the open questions begin. One line of thinking holds that pressure alone, if evenly distributed through a body with no trapped air, would do less damage than people assume. Water inside cells does not compress the way air does. Some researchers point to fish and invertebrates living quite calmly at these depths as proof that pressure by itself is survivable given the right biology. Other researchers push back, noting that human bodies carry air spaces, lungs, sinuses, the middle ear, that would collapse or rupture long before the pressure reached its full weight. Which failure would come first, and how quickly remains something researchers can model but never fully test, because no one has gone there unprotected, and no one plans to. The trench itself formed through a different kind of math, one written in millions of years instead of meters. It sits at a subduction zone, where one section of ocean floor slides slowly beneath another, sinking back into the deeper layers of the earth. This process bends the seafloor downward into that long scratch on the map. Some geologists estimate the trench has existed in something like its current form for tens of millions of years, though the exact age remains debated, since the rock at the bottom is old and difficult to sample cleanly. The trench is not a static wound in the ocean floor. It is a slow, ongoing motion, still happening today, too gradual for any human eye to see directly. If you dropped a weighted marker from a boat above the Challenger Deep, it would fall for more than an hour before touching the sediment below. During that fall, it would pass through nearly every pressure zone that separates surface life from trench life, a journey your own body could never make, and return from unharmed. The distance is measurable. The time is measurable. What is far less certain is exactly how life adapts to survive down there, cell by cell, and whether the same rules would apply to a body built like yours, dropped into that same math, with no protection at all. The numbers are precise. The living answer underneath them is still being worked out. If you sat and thought about it for a while, a strange fact might settle over you. We have better maps of the moon than we do of the ocean floor beneath the Mariana Trench. You could name the craters of a place 250,000 miles away, more easily than the deep trenches a few miles beneath a ship's hull. This is not because the moon is simple. It is because the deep ocean is far harder to see. Light is the reason. The moon reflects sunlight freely, with nothing in the way. A camera in orbit can look down and capture every ridge and shadow in clean, sharp detail. The deep ocean offers no such gift. Sunlight fades within the first few hundred meters, and by 1,000 meters down, it is gone entirely. Below that, mapping the seafloor means bouncing sound waves off the bottom and waiting, sometimes for seconds, for the echo to return. It works, but it is slow, and it is imprecise compared to a photograph taken in full sunlight. Pressure adds another layer of difficulty. A satellite orbiting the moon faces no crushing force, no corrosive salt water, no near freezing cold. A vessel probing the Mariana Trench must survive pressure 11,000 times what you feel standing on a beach. Every camera housing, every sensor, every seal has to hold against a force that would flatten an ordinary steel drum like a piece of paper. If you tried to lower an unprotected instrument to that depth, the water would find any weakness within moments and fill the gap with cold, dark seawater. This is part of what makes the deep ocean feel like the more foreign place, even though it sits just beneath the waves we swim in every summer. The moon is close in the sense that we can see it, plan for it, send instruments toward it with a clear line of sight the whole way. The trench is close in the sense that it is only a few hours from a coastline, yet reaching its floor means moving through total darkness, crushing pressure, and near-freezing water for the entire descent. Distance is not always about miles. Sometimes it is about how hostile the space between 2 points turns out to be. Some researchers frame this as a question of cost and priority rather than difficulty alone. Lunar mapping missions have had decades of funding, driven partly by the drama of space exploration and the promise of future travel there. Deep ocean mapping has drawn less sustained attention, even though it maps a place that touches every coastline on Earth. One view holds that if the same resources spent studying the moon had gone toward the seafloor instead, we might already have full and detailed maps of every trench on the planet. A competing view points out that the moon's environment is genuinely easier to work in, and that even a well-funded ocean program would still face the basic physics of pressure and darkness that make deep water research slow, no matter what. There is also the matter of what a body could tolerate in each place. Step outside a spacecraft on the moon without a suit, and the danger comes from vacuum and radiation and extreme temperature swings. Sink to the floor of the Mariana Trench without protection, and the danger begins immediately with compression, a force pressing in on every part of you at once, long before cold or lack of air would even become the concern. Neither place allows an unprotected human body to survive for more than a few moments. But the moon has been walked on. The deepest trenches have been visited by only a handful of people in armored vessels for a matter of hours across all of human history. If you tried to picture the whole of the seafloor mapped in the same fine detail as the lunar surface, you might picture something like a fully lit photograph, ridge by ridge, trench by trench. That picture does not exist yet. Large sections of the ocean floor remain sketched only in rough outline, known mostly through sound and inference, rather than direct sight. Whether that gap closes in the coming decades through cheaper submersibles or new sonar technology, or whether the deep ocean keeps its advantage as the less mapped, less visited place, is still an open question. For now, the moon above you is better charted than the water beneath the deck of a ship crossing the Pacific. If you stood at the rail of that ship, the trench below your feet would remain, in a very real sense, less explored than the pale surface hanging in the night sky above you. Picture yourself floating quietly above the trench, imagining the water beneath you as something almost solid, a wall of pressure 11 kilometers thick. From up here, it looks calm. Down there, that same water pushes back against itself in ways researchers still do not fully understand. The ocean, it turns out, resists study the way it resists intruders. It does not give up its secrets easily, and some of its deepest questions have stayed open for decades. One of those questions is simple to ask and hard to answer. Why does life not just survive the trench, but seem to need it? Certain amphipods and worms found at the bottom cannot live at shallower depths. Bring them up even partway, and they weaken, then die. Some researchers think their cell membranes and proteins have become so finely tuned to crushing pressure that normal ocean conditions feel wrong to their biology, almost foreign. Others wonder if it is less about needing the pressure itself and more about avoiding competition, since fewer creatures can reach that far down to compete for food. Both ideas are reasonable. Neither has been proven, and that gap sits quietly at the center of trench biology. The chemistry of the water itself raises questions too. At those depths, cold temperatures combine with enormous pressure to change how gases dissolve, how minerals form, how quickly organic material breaks down on its way to the floor. Some particles that would decompose quickly near the surface survive much longer in these conditions, sinking for weeks before they land. Researchers are still mapping how this slow, cold chemistry shapes the strange food web living down there. You would feel none of this happening around you if you were somehow present, only the steady, silent pressure against your body, indifferent to the reactions occurring at the molecular level. All around you, sound is another unresolved thread. Hydrophones lowered into deep trenches pick up sounds scientists cannot always identify. Some are almost certainly geological, the shifting of rock or gas escaping from vents. Others resemble nothing in the existing catalogue of ocean sounds, whale calls, ship engines, or seismic activity. A recording made in the Mariana Trench years ago, sometimes nicknamed for its strange metallic quality, remains only partly explained. One theory points to ice cracking somewhere far off. Another suggests an unknown biological source. The recording exists, the explanation, fully agreed upon, does not. Then there is the matter of scale. Only a small fraction of the deep trenches around the world have been mapped in detail, and only a smaller fraction than that has been visited by any vehicle, human crewed or robotic. Each new descent tends to reveal something unexpected, a vent no one predicted, a creature with no name yet, a shift in sediment that does not match older models. If you multiply that pattern across every trench on Earth, most still unvisited, the size of what remains unknown becomes almost impossible to hold in your mind while floating here at the surface. Some researchers describe this as the ocean's own form of resistance, not hostility exactly, but a kind of structural privacy. The same pressure that would crush a human body also limits how often instruments can be lowered, how long submersibles can stay, how much data any single expedition can gather. Each visit is expensive, brief, and physically demanding on the equipment involved. That means progress happens in small, careful steps rather than sweeping surveys, and each step raises nearly as many questions as it answers. There is also the deeper, more philosophical uncertainty underneath all of this. Some scientists ask whether we are even looking for the right things down there, since our instruments and expectations were built based on life we already know from shallower water. If something entirely different in its biology or chemistry exists deeper in the trench, we might not recognize it as unusual, or we might miss it completely, mistaking it for sediment or noise. That possibility remains speculative, but it lingers at the edges of many deep-sea papers, an acknowledgement that the tools we have may only reveal the mysteries shaped like the ones we already expect. If you lowered your hand into water at that depth, and if your body could somehow survive it, you would feel no resistance from your muscles fighting to keep you afloat, only that patient, total pressure meeting you evenly on every side. It would ask nothing of you and reveal nothing to you either. The trench keeps its questions the same way. It keeps everything else down there, sealed beneath kilometers of dark, cold water, waiting for whoever finds a way to ask again. If you had lived 1,000 years ago, near any coast, you would have heard the old stories. Sailors spoke of monsters below the waves, of places where the water swallowed light and never gave it back. You would have felt that same small fear in your chest, standing at the edge of a dark harbor at night, listening to water you could not see move against the rocks. That fear was not foolish. It was, in its own way, an early kind of science. Long before anyone measured pressure in atmospheres or drew a map of the Mariana Trench, people understood the ocean had a bottom they could not reach. They built their fears into shapes, krakens, leviathans, doors to the underworld hidden beneath the swells. These stories were not about biology or physics. They were about the same fact we still sit with tonight. The deep sea was, and still is, a place the human body cannot enter and return from unaided. What is interesting is how little that fear has actually resolved, even now. We have replaced krakens with hard numbers. We know the pressure at the bottom of the trench is about 11,000 times what you feel standing on land. We know the temperature hovers just above freezing. We know there is no light, not dim light, but the complete and permanent absence of it. And yet, the feeling those old sailors had, the sense of standing at the edge of something the body was never built for, has not gone away. It has only become more precise. Some researchers think this old fear served a real purpose. A species that respected the deep water, that stayed near the surface and passed down warnings, may have simply survived better than one that did not. Other researchers are less sure the myths tell us anything about survival at all. They point out that fear of deep water shows up in cultures with very different relationships to the sea, some who fished those waters daily, and some who rarely touched them. The pattern is there, but why it is there remains an open question. If you stood on a rocky shore at dusk, watching the water darken as the sun dropped, you would feel your own small version of that old unease. It is not really about monsters. It is about scale. The ocean is large enough and deep enough that a very human part of you understands it does not need to threaten you directly. It only needs to be indifferent. The trench does not wait for anyone. It simply exists, 11 kilometers down, holding its pressure and its cold and its darkness. Whether or not a single boat ever crosses above it, what will happen to this fear and this mystery across deep time is its own kind of open question. In a million years, the trench itself will still be there, though slightly different. The Pacific Plate continues its slow crawl, carrying the Mariana Trench with it, millimeters each year, the same pace at which your fingernails grow long. After every current fear and every current myth has been forgotten, the physical fact of the trench, or something like it, will likely remain. New trenches may form elsewhere, as one plate continues sliding beneath another. The deep ocean, as a category of place, appears to be a permanent feature of a planet with plates and water. That much seems durable. What is far less certain is whether the fear softens or simply changes shape. Perhaps future explorers, with better machines and deeper knowledge, will feel less awe and more familiarity, the way we now feel about mountains once thought unclimbable. Or perhaps the opposite happens. The more precisely we measure the pressure, the temperature, the crushing weight of 11 kilometers of water above a single point, the more that old feeling in the chest might sharpen rather than fade. Facts do not always dissolve wonder. Sometimes they give it better footing. You can feel a small trace of this tonight, lying still, thinking about a place your body could never reach on its own. It is not a modern feeling. It is a very old one, passed down through generations who stood at different shores, looking at the same dark water, wondering the same unanswered thing. The trench does not know it is feared. It does not know it is measured either. It simply sits at the bottom of the world, 11 kilometers down, doing what it has done for millions of years, patient in a way nothing living can be. Whether our fascination with it changes across the centuries ahead, or whether it stays exactly as old and as quiet as it has always been, is something none of us can say for certain yet. If you imagine standing at the rail of a research ship 100 years from now, you might feel the same salt wind on your face that sailors felt a century ago. The ocean itself will not have changed much. What waits below it might still be almost entirely unknown. Even then, think about how young this kind of exploring still is. Humans have only visited the deepest part of the ocean a handful of times. Compare that to the thousands of years people have watched the stars, named them, built stories around them. The bottom of the Mariana Trench has been touched by human eyes maybe 5 times in all of history. Some researchers wonder if future explorers will find it strange that we reached the moon before we reached our own ocean floor with any regularity. Others say the comparison is not fair. Space is empty and predictable. The deep ocean is full of crushing, moving, living complexity. The question of which frontier is truly harder remains open, and maybe it always will. If you could send a message forward to whoever explores the trench 100 years from now, you might ask them what they found in the sediment. That soft, undisturbed floor has been collecting the slow rain of material from above for millions of years. It holds a kind of memory, ash from ancient volcanic eruptions, the shells of creatures long extinct, chemical traces of events on the surface that happened before humans existed. Future scientists with better tools might read that mud like a book, page by page, pulling out a record of Earth's past that we can only guess at now. One theory is that the trench floor holds clues to ancient climate shifts, preserved by cold and darkness and pressure. Another is that so much of that record has already been scrambled by burrowing creatures and slow currents that it will never be fully readable. Nobody knows yet which is closer to true. Consider, too, the creatures. The ones we have found so far, the pale fish, the strange snailfish, the amphipods drifting through absolute dark, all of them are built around this crushing pressure rather than in spite of it. If you brought one to the surface, its body would fail long before it reached open air. Future explorers might find entirely new species we have not imagined, forms of life shaped by chemistry we do not yet understand. Some researchers wonder if the trench holds biological answers relevant to life in other extreme places. Distant ice moons, perhaps, if the parallel and survival strategy holds up under closer study. Others caution against reading the deep ocean as a stand-in for anywhere else. It is its own place, shaped by its own long history, and comparisons might tell us more about our need for connection than about the trench itself. There is something almost calming in realizing how much is still unknown. If you stood on that ship rail again, feeling the wind, you might notice how small your own certainty feels next to that dark water. The largest habitat on Earth, by sheer volume, is the deep ocean, and most of it has never been seen by any human eye. That fact alone tends to soften a person's sense of how well we know our own planet. Future explorers will have quieter submersibles, stronger materials, better cameras. They may map the trench floor in detail we cannot picture yet. But the pressure will still be the same, 11,000 times what you feel right now, breathing easily in open air. No engineering improvement changes that number. It only changes how carefully we learn to work around it. Maybe what future explorers find will not overturn everything we think we know. Maybe it will simply add detail to a picture that is already mostly correct. Or maybe there is something down there, some chemical process, some form of life, some pattern in the sediment that reshapes an entire field of study. Both possibilities remain open, and there is no way to know in advance which one is waiting. That uncertainty is not a gap to be nervous about. It is closer to a kind of patience, the way a slow tide moves without hurry, without needing to prove anything tonight. If you let your body settle into that thought, the not knowing starts to feel less like an absence and more like room to breathe. The trench will still be there tomorrow, holding its darkness and its pressure and its slow falling snow of ancient material, waiting the way it always has. Whatever future hands and lights and machines eventually find there, they will only be adding one more layer to a mystery that began falling into place millions of years before anyone was around to wonder about it at all. If you stood on a beach tonight, the ocean would look calm, flat and dark, maybe touched with a little moonlight on its skin. You would have no way of knowing that under that quiet surface, 11 kilometers down, there is a place your body could never visit and live. Not because the water is too cold, though it is. Not because it is too dark, though it is that too. It is because the water itself, at that depth, presses down with a weight your cells were never built to hold. We have spent this long night thinking about that pressure. 11,000 times what you feel right now, lying still, breathing easy. We have imagined the long fall through darkness, hour after hour, past the last trace of sunlight, past the last fish shaped like the ones you might know, down into a place where the water is just above freezing and has been that way for longer than there have been humans to wonder about it. We have thought about the creatures down there, built not to survive that pressure, but to need it, falling apart if they ever rose too high. We have thought about the submersibles, their metal hulls groaning quietly under a weight most of us will never feel. And still, after all of it, the question stays open. We do not fully know what lives in every fold of that trench floor. We do not know how many species have adapted to that darkness without ever being seen. Some researchers believe the deep trenches hold thousands of undiscovered organisms, cousins to creatures we have only glimpsed in passing. Others believe we have already found most of what can survive there, and the rest of the darkness is simply empty, sediment and silence, falling snow that has been falling for millions of years. Both ideas stay alive tonight, resting side by side, unresolved. That is a strange comfort in its own way. A planet this old, this well-mapped, this covered in satellites and cables and ships, still keeps a room nobody has fully seen. The bottom of the sea is closer to you tonight than the surface of the moon is to the astronauts who touched it, and yet in some ways it remains further away, less understood, less visited. We have walked on the moon more times than we have reached the deepest point of our own ocean floor. That fact alone is worth carrying gently into sleep, not as something to worry over, but as something to feel small and quiet beside. Picture the trench now, one last time. No light, no sound, but the low groan of the earth's plates shifting somewhere far off, and maybe the far-filtered call of a whale passing overhead, its voice traveling farther through water than it ever could through air. The floor is soft. It has been building for ages, one thin layer at a time, undisturbed by storms or tides, or anything from the world above. It does not know that we exist. It has never needed to, and yet you are connected to it in the plainest way. The same ocean that laps at a warm shore in summer reaches, without a single seam, down into that frozen dark. The same water, the same planet, the same slow, patient system that keeps you breathing right now, keeps that trench exactly as it is, pressing gently on creatures who have never known anything else. You do not need to go there to be touched by it. You are already part of the same skin of water and stone that holds that darkness far beneath your feet. Let that be the last thought tonight. Somewhere below the calm surface you might imagine, in absolute cold and absolute dark, the ocean is quietly doing what it has always done. It is not waiting for us. It does not need to be solved tonight, or ever. It can simply be there, holding its mystery the way it holds everything else, patient and enormous and calm. You are safe in your bed, warm under your blankets, far from that pressure and that cold. The trench will still be there tomorrow, keeping its secrets a little longer. The world is vast, but you do not have to carry all of it. For tonight, it is enough to know it is there, turning slowly in the dark, asking nothing of you at all. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.